So over the year then, I had several meetings with Penny and Richard, where each time I would try and refine the requirements, go off, work on the concept a bit more and come back and then show them what I'd done. And then they would, I was very open to criticism about how it could be amended further based on the time that I had left on the project. And by the end, we got to this point in July 2022, where I had my finished technical design. So the SATCO, which so the device for the SATCO in front of you, which I'll demonstrate on one of the later slides, a video of how it works. But the arms that grip the side of the child needed to have a big enough variance that it could support either a toddler or a fairly big 16-year-old child, with weights ranging from, if I remember, something like 20 to 120 kilograms. So obviously very different sized patients need to be able to use the same machine. So the arm variance is 220 millimeters. The amount that it can vary up and down the spine is 192 millimeters. And the backrest, which pushes into the back, into the spine at a point, can be pushed forwards or backwards 130 millimeters. These are the main components that were designed to assemble the whole thing together, excluding the electrical components in these drawings. So the main base supports, the whole device is supported and attached to that. The arms are to pick up the child. The electronics frame mounts all of the electronics to the center column, and the center column connects the body of the machine together. The back mechanism elongates and pushes into the patient's back to keep them steady. The actuator mount or piston mount allows the piston to feed through it, connecting to the base and the center column. The wings are to allow the arms to slide along and to retract when unlocked. The sliding socket it has wheel bearings on it so that it can slide along the inside of the wings. The arms actually have force sensors inside them so that the device knows when it has contacted the side of the child. And the wing socket and arms all have mirrored versions of themselves that aren't shown in this diagram. And the gear system is to hold the lock in place and ensure that the wings retract symmetrically, so that all the physiotherapists would have to do is pull one side and it will pull back equally on the other side. So over the course of the project, I modeled 59 parts and prototyped a few more. So I worked out that by the time I built the thing, I had printed over 100 individual parts. Just one example of the force body considerations that went into the project to make sure that the device wouldn't tip forward. So based on the forward pivot point and backwards pivot point, the device and the expected weight that a child would put on the machine, as I said, either a small child of 20 to 30 kilograms or a big one of 120 kilograms. The device should, based on the base, support the weight. So the next thing to mention is obviously the electrical circuit. The splitter that you can see on the top left-hand corner ensures that every component has access to power. It splits 4 ways between the Arduino, 2 motor drivers, and the relay lock. The single end of the splitter will connect to a transformer that will be connected to the mains. The Arduino is the circuit controller responsible for controlling the pistons and locking mechanism based on both user inputs and data from the force sensors. The 12-volt adapters allow the motors and locks to be wired to the splitter. The motor drivers allow the linear actuators or pistons to connect to the Arduino, and they provide the piston with control power and interface with the Arduino via pulse width modulation. 2 pistons can be connected to 1 motor driver. The height pistons are responsible for the varying of the machine up and down, and then the arm pistons are responsible for the width variance around the patient. The force sensors will be underneath the cushions, so they're pressing against the patient's side, and as you can imagine, if the force reads too high, then the lock will retract, releasing the mechanism from the child. The lock, so when it retracts, again, using the gears, it doesn't just do one side and then the other, it's both of them symmetrically. So the relay is necessary to correctly power and control the lock, and the relay interfaces with the Arduino using an analog data line. A USB was then connected to my laptop, which allowed me to program some controls that I could then test to make sure that all of the components were working properly. The software that I developed on my laptop was quite basic, but I needed some C++ that I would put on the Arduino, and then I made another C# application using just a Windows form so that I could test it. In future, you could connect the USB to a set of pedals or buttons or so on, but that was kind of outside the scope of the time that I had. The movement, process and flowchart that you see in front of you, though, is the C++ that I wrote. So basically, you can see that it turns on, it waits for a user input, whether that is raise the height or lower the height, widen the arms or tighten the arms, or open the lock. And opening the lock doesn't have to be manual, because if the force sensors are reading too high, indicating that there is a potential danger to the child, then that will also stop the machine as well. So this is it in practice once it was assembled, sped up, but as mentioned again, the range in height is 192 millimeters. The arm variants, which I'll show you on the next slide how this actually works inside the machine, again has a variable range of 220 millimeters. And on Fusion 360, where I developed it, you can see how the actuators drive the sliding sockets along the inside. Currently, I designed the backrest to be just manually mechanical. In future works, you could probably put a servo motor inside so that that is also controlled electronically as well. The locking mechanism, which you can see at the top of the image on the left, just inside above the electronics, catches the lock when it's retracted. So if you can see, when the center gears are all the way down, there's a hole there that the lock could go around. Unfortunately, it didn't work out as well as I would have liked it to, because I was conveniently sent the wrong type of lock during the project, so it didn't click into place. I needed to unlock it, move it, lock it again, but in some sort of future works that would be amended. And the arms retract 30 degrees each, which is an appropriate amount so that it's far enough away from the child, but also they're not swinging into the side of the physiotherapist. So with all that said, this video just demonstrates the motions that you would see in a SATCO assessment. So you can imagine the physiotherapist is sitting behind, The child is sat facing the camera on the bench, and the machine would gradually go down, support them by their sides. The physiotherapist would then test that part of their trunk, go down, grab again, test, and so on. That's what that motion represents. So finally, nearly just out of interest for you, you can see the price of the whole thing, which came to about £700. I was conscious to make sure that all of the materials that I was using and electrical components were either reusable or recyclable at the very least. The price would go up in a future work of this project if stronger materials were used, because as I mentioned earlier, additive manufacturing is very good for quickly testing the geometry of things, and it can be very hard, I found, when designing something to consider absolutely everything mechanically without actually having some real hands-on experience with assembling things. So there were a few bad designs that were amended, and there are definitely, in the prototype that I built, parts that would in future need to be metal perhaps, or carbon fiber, or so on. So a future model would be more expensive, but I'm satisfied that the geometry has mostly been accounted for. So almost lastly, the main problems encountered were availability with the printers, because it is a university facility, and though there were a lot of printers, there were also a lot of people doing projects at the same time. The strength of the prototype, as just mentioned, though in the video you can see it working, that the motions are what would be required, they're not quite strong enough because they are made of PLA plastic. The Arduino unfortunately broke before I was able to test it properly. So though I got ethical approval to test it on a healthy adult, it never made it to that point. Another reason being that the force sensors were faulty, and by the time that I had left Manchester and was assembling it, there wasn't much I could do about that. But it's quite documented what the problem was, so that shouldn't be a problem in future, hopefully. So some future works, mechanical changes, so again, stronger materials, maybe some slight changes with the geometry of some of the parts, but mainly plastic to metal considerations. Also, the ability to attach it to the desk more efficiently. At the moment, it would be done using some sort of ropes, which there are attachments for, but something a bit more permanent would be a better solution. It's not currently waterproof, which in a medical setting could pose a problem. And though additive manufacturing was quick and cheap and effective, some parts are just better and stronger and easier to produce using original reductive manufacturing. So, you know, as we progress into the future, I feel like most products will have a mix of both types. So soldering the force sensors, that was really one of the main problems that I just mentioned. They kept coming loose. If they were actually soldered, the circuit would have been a lot more reliable. Again, a servo motor inside the back mechanism. And currently, the device needs to be connected to power to be able to release the child, but throughout the meetings that me and Penny and Richard have, we did often discuss some sort of backup mechanism that would, in the event of power failure, it would spurt some energy into it so that child could be released safely.